Okay, so this is the second lecture for Wednesday the 22nd, and we're covering 9.3 exponential functions as well as homework 21B. So exponential functions are a new type of function. We've covered linear functions, absolute value functions, quadratic functions. Exponential functions are defined by the fact that the variable is in the exponent. So for a general form, an exponential function will look like this. You'll have a base, and that base will then be raised to the variable x. So there's your exponential function. Sometimes the base is also multiplied by something, so sometimes you will see it with a number out in front. It's also possible that you could see some horizontal and vertical shifts. So you could see values up in there with the x, or you can see values added on afterwards. But we're just going to do a very basic overview of what are exponential functions. So first off, for MyOpenMath, the first question that you have is just to be able to identify what does the graph of a function like this look like, okay? So let's say, for instance, you have the equation y is equal to 6 to the x power. What does the graph of this look like? What do people say when they say that something is increasing exponentially? Now, in looking at the graphs of COVID cases online, you're going to see this exponential growth. So over time, the COVID cases on a calendar, they started off really small in the U.S., and then all of a sudden you see that the COVID cases are going up. And so they have little rectangles underneath for how many cases were diagnosed on which day. And you see that the cases just start shooting up really fast. And when that shoots up really fast like that, that is called exponential growth. So we see that the number of cases of COVID-19 in the U.S. have been exponentially increasing. That's how it just exploded so fast. And that's exactly what the graph would look like of a basic exponential function like y equals 6 to the x. It's going to look like this. So graphically, in terms of having an xy plane, your picture is going to look like this. Okay, so on MyOpenMath, question number 1, you just need to match a basic exponential graph, a function to its graph, and this is the graph that you would choose. Now, if the value here for the base is less than 1, it's a little different. Here, this is exponential growth. Okay, so if the b value is greater than 1, then this is called exponential growth. But there's also the case where you could have what's called exponential decay. And we see this in other contexts, such as you put caffeine into your bloodstream, and it's going to decay in your bloodstream over time. How much caffeine remains in your bloodstream, or any drug that you put into your body, the amount that still remains active in your body is going to decay over time. And so you'll see a different type of function. And so it will look like this. If you had the function y is equal to 1/2 to the x power, here you see that b is less than 1. It's still a positive number, but it's less than 1. The graph of this function, and this is question number 2 on MyOpenMath, is going to look like this over time, okay? And this is called exponential decay. So when the graph goes down over time, that's because the base is between 0 and 1. But when the base is bigger than 1, then you're going to see exponential growth. So now let's look at question number 3. On MyOpenMath, question number 3 gives me a exponential growth function, a really simple one. And then there's an xy table, and the values of x are already plugged in for you, 0, 1, and 2. So you just need to plug these values in here, okay? So 2 to the 0 power, plug in 0 for x. 2 to the 0 power is 1, right? So that's a f of 0. Then you have plugging in 1. F of 1 would be 2 to the first power. And then f of 2 would be 2 to the second power. And when you go to graph this, you only have to plot 2 points. The exponential curve will already be selected there for this question, so you only have to plot 2 of the points and then it will graph it for you. So you might want to graph the point 0, 1. Graph the point 0, 1, and then you graph just one other point. I might graph 1, 2. If I graph 1, 2, the curve on MyOpenMath will automatically fill in for me an exponential graph. So this one's pretty simple like that. So then when you get to question number 4 on MyOpenMath, you're going to be given a slightly more complicated equation. In my version, I have 4 times 3 to the x. Now remember, in PEMDAS, exponents come before multiplication, okay? So if you're evaluating this graph, right, f of 0, f of 1, and f of 2, what do they look like? Well, each of them still have a 4 out in front. 4 times 3 to the 0, 4 times 3 to the 1, 4 times 3 squared. You always take care of exponents before multiplication. So 3 to the 0 is 1. 1 times 4 is 4. So this is not 12 to the 0 power. It's 3 to the 0 power times 4. This one is 3 to the first. 3 to the first is 3 times 4 is 12. And then here, 3 squared is 9. 9 times 4 is 36. And then you just graph 2 of these points. Just graph 2 of those points and the rest of the graph will be done for you. So for question number 5, you don't have to graph, you just have to fill in the table. But this one's a little different because we have a decimal. Still exponential growth. Notice 1.6 is still greater than 1. So we still have exponential growth. So for each of these, you're going to evaluate, so you're going to end up with 100 times 1.6 to the 0 power, 100 times 1.6 to the 1 power, 100 times 1.6 squared, 100 times 1.6 cubed, 100 times 1.6 to the 4th power. So 1.6 to the 0 power is still 1. 1 times 100 is 100. 1.6 to the 1 power is 1.6. 1.6 times 100 is 160. And feel free to use the calculator. 1.6 squared is 2.56 times 100 is 256. And at this point, I would start using the calculator. Type this in the calculator and you get 409.6. Type this one in the calculator and you get 655.36. So a simple, just plugging it into the calculator. If you're using a graphing calculator, your graphing calculator will automatically follow PEMDAS for you. Okay, so now I want to look at some word problems. First, let's look at some radioactive decay. On page 786, number 47 has radioactive decay. Now, I'm going to make up a problem that's similar to number 47. Okay, suppose the amount of a particular substance after a number of, let's do years. If the initial amount of a substance is maybe like 300 grams and it decays over time, maybe 1/4 of that amount per year, and we want to figure out, okay, how much of this substance is left after 10 years. So if you want to know how much of the substance is left after 10 years, knowing that A represents the amount in grams of the substance, and in this case T represents time in years, so you just have to plug in, so after 10 years you're going to look at A of 10, which would be 300 times 1/4 to the 10th power. So you just type that in the calculator. I made this completely up, so this is not that hard. You just take 1/4, raise that to the 10th power on your calculator, and then multiply that by 300. And it says to round to the nearest 1/10 of a gram. In my case, because this one decays so rapidly, it actually ended up being 2.86, and then it says E -4. What that means is to the -4th power. So this is actually written in scientific notation. So that would be 2.86 times 10 to the -4th grams. If you write that as a decimal, that's 0.000286 grams. The place that I would round to in this problem is not going to be identical to the rounding for number 47. But for number 47, just make sure you check your answer in the back of the book, and then you'll know also where you're supposed to round to. But the work is simple. Just replace time with what time you're given, 10 years. Replace time, and then you just type it in the calculator, and you'll come up with your answer. So you just have a one exponential decay problem, and then the other use of the exponential function we're going to look at is exponential growth for money. So you see that with compound interest. Now the compound interest formula is provided for you on page 781. So on page 781, you have this compound interest formula, which is that the amount in an account over time is equal to the principal times 1 plus the interest rate divided by n all to the nt. So what does this all represent? So A is the amount after t years, and that amount is going to be in dollars. P is the principal. The principal is the same thing as the original money that was deposited or invested. R is your interest rate, and you need to write your interest rate as a decimal. T, of course, is the number of years, and then N is the number of times per year you're compounding. So, for instance, if you were to compound every month, monthly compounding would be that you're breaking a year into 12 increments. So N would be 12. If you are doing a quarterly compounding, you break the year into four sections, and so N is 4. If you are compounding daily, there are 365 days in a year, so N would be 365. So now if we look at MyOpenMath, we're going to have a problem that's going to use this formula. So in MyOpenMath, problem number, let me pull one of these up here. This is compounded weekly on question number 8. So question number 8, it says find the final amount of money, so that would be the amount in the account, in an account if $3,200 is deposited. Okay, so we want to find A. We know that the original amount of money that's deposited is $3,200. It's deposited at 8%, so that's your R value. R is 0.08. And then that is compounded weekly. So compounded weekly means that N is equal to 52, since there are 52 weeks in a year. R is equal to 0.08 because 8% as a decimal is 0.08. And then we're told that the money is left for 7 years. Okay, so if the money is left in the account for 7 years, T is equal to 7. So what I do is I just take this original equation here. I replace P, the original amount invested, with 3,200. Rate I have as a decimal, 0.08. I'm dividing that by 52 because I'm compounding weekly. And then I'm raising this to the n times t power. So that would be 52 times 7. Now, when you type it in the calculator, make sure both the 52 and the 7 are in the exponent. You might have to use parentheses depending on the way your calculator is, the syntax shows up. You just make sure that the 52 times 7, both of those end up in the exponent. So try doing this problem, this particular problem, type it in the calculator, and make sure that you can get the exact answer that I get, okay? So if you take 3,200 and you multiply that by 1 plus 0.08 divided by 52, and you raise that to 52 times 7, and you push enter, you're going to round to the nearest cent. It's not going to tell you that, but in general, you round to the nearest cent. Oh, actually, no, it did say round to 2 decimal places. 559974. So after 7 years, if you have an 8% interest rate, which of course right now we have like near 0, at 8%, actually we do, right? The feds have lowered it to 0%. Here, the amount in the account is 559974. So that is a compounding interest problem. And you're going to do a couple different compounding interests. So in the case of the 9th question, which has a video, so if you need to watch the video, you can, you're going to compound annually, which means that n is equal to 1, semi-annually, so n is equal to 2, monthly, n is equal to 12, and daily, n is equal to 365, and you'll get to do a problem you'll do it 4 different ways. And so there's a video that can walk you through that. And then also from your book, you need to do a compound interest problem from 9.3. It's number 55. So you're going to look at 2 different investments, and you're going to compare the interest rates for those. So you actually have several compound interest problems to do. It's actually one of the most handy, it's very accessible, right? We think about money, we think about compound interest, we invest. This is one of those life skill things to understand, and it's pretty central to compound interest that you understand exponential functions. So you can explore exponential functions by learning compound interest. So that's why you have so many problems of those to do. All right, that wraps up this lecture, which covers 9.3 and homework 21B. And next, we're going to move into the next sections, which cover from 9.4 all the way into chapter 10 and homework 22. That will be the 3rd lecture for Wednesday, the 22nd.